Good afternoon. Welcome to today's SCA webinar with Dr. Siddharth Misra on machine learning for subsurface characterization. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. So I'm going to launch some polling questions. The first question is, what is your primary discipline? We have responses coming now. Looks like a pretty even split between geoscientists and petroleum engineers. We've got a few in the other category. So it looks like most of you have voted. I see 59% geoscientists, 37% petroleum engineers. So I'll share those results. And then I'm going to go to our next question. How many years of full-time experience do you have in the upstream oil and gas industry? It looks like we have some in every category. Responses are coming now. Looks like we've got 37% in the 11 to 20 year group and a good spread over the rest of the categories. Most of you have voted, so I'll go ahead and share those results. And we'll get started. Before I introduce Sid, I'd like to remind the audience that you're muted, but you can ask questions today using the GoToWebinar question feature, and we will cover the Q&A at the end of the presentation. You will be anonymous. So today's webinar is machine learning for subsurface characterization. Dr. Sid Misra is our speaker. Sid is a professor at Texas A&M in the Department of Petroleum Engineering. He has a joint appointment with the Department of Geoscience and Geophysics at Texas A&M. He is a well-known subject matter expert in the field of subsurface monitoring for exploration and production of subsurface Earth resources. He has authored 2 books, Machine Learning for Subsurface Characterization and Electromagnetic Data Interpretation for Subsurface Characterization. Sid started his career at Halliburton. In 2018, he was recognized with a DOE award for early careers, and he has contributed to the disciplines of geophysics and subsurface engineering, and thus received several awards, including SCG's Karcher Award, SPAA's Young Professional Technical Award, the SP Gulf Coast Section Formation Award, and the EIG Ari Van Wielden Award. He holds a BS in Technology and Electrical Engineering from the Indian Institute of Technology in Bombay, a PhD in Petroleum Systems and Geosystems Engineering from the University of Texas at Austin. So Sid teaches a course for SCA that will be offered in a public format in January in Houston in SC's office. The course description is listed there, and you will see a sample of this material in today's webinar. Of course, this can also be offered in a private class in-house or perhaps even in a virtual format. So contact our training department for that information. We have several live online classes that are being offered in virtual formats. The next few that are coming up include a CCUS class with a geological perspective that's offered by Dr. Steve Sonnenberg, production forecasting for low perm reservoirs offered by Dr. John Lee. And in November, we have a CCUS with an engineering perspective offered by Dr. Christine Economides and Dr. Dimitrios Hazignatou. Look for those on SCA's website. We have 2 webinars that are just around the corner. Coming up at the end of September, Rob Pascoe will be speaking on the carbon sequestration potential of the Louisiana-Texas shelf, Gulf of Mexico. And Salim Shaker will be speaking in October on pore and geopressure prediction framework and applications for exploration and production. Of course, SCA training courses can come to your location if you'd like to schedule a private in-house training or one of those virtual live online classes. Here's some contact information that you can get in touch with our training department. And we do offer discounts for those who are in a career transition. And choose SCA when you think about not only training, but consulting, projects and studies, and direct hire staffing for both contract and full-time employees. And with that, I'm going to hand over the presentation rights to Sid. Sid, it's all yours.
Thanks a lot for that introduction. And just a quick check. Do you see the whole screen? Do you see the browser that I'm sharing?
Yes.
Okay.
We can see it. And we see your video as well.
Great. So hello to all of you. I see there are around 50 participants today. So the whole objective of today's discussion is to share some very basic machine learning type of workflows that we can use. And all my courses that I teach are pretty hands-on. What I mean by that is I don't use PowerPoints. Rather, what I do is I use a Jupyter Notebook environment, which helps me interactively change the code and show you how the different parameters and changes affect a machine learning workflow. So with that, there's a course content that I kind of follow when I teach the courses with SCA, and I'm taking snippets from this entire 2-day long course, and I'm showing you some snippets. There is 2 projects that follow this course. So after you get trained for 2 days, there'll be 2 projects, one on production forecasting and the other one on shale image analysis. So I'll take, let's say, 30 minutes of your time and show you some snippets from these 2-day courses followed by projects. Now, I won't be explaining what's going on. I won't go deep, because if you want to know all the concepts, all the foundations, then I would encourage all of you to attend the course. But let me give you a quick workflow, how we can develop a simple machine learning workflow for classification and then for a regression. We need some packages. What you see here is a Jupyter Notebook environment, and I'm importing 4 packages: NumPy for linear algebra for array manipulation, pandas for working with tabular data. So instead of using a Excel file, you will use pandas to import the data and work with tabular data. Then for visualization, we have matplotlib, and for enhanced plotting, we have Seaborn. So these are the 4 packages. I will get these packages into the Jupyter Notebook environment. And now I'm ready to import a small sample data set, which will help us perform a classification task. So this is the data set, which is sample_class.xlx. There is a particular sheet that I want to import, and the sheet is well2. Because of the constraints in time, I cannot show you how this data set looks like, but let me just import it and show you in the Jupyter Notebook environment. So there is a pandas functionality called read Excel. I'll use that to import this data set, and then I'll show you how the data looks like. So the data is pretty simple. We have a depth, then we have the well number, so this is the well ID. Then we have 4 logs: gamma ray, resistivity, bulk density, neutron porosity, and then there is a facies label that was assigned by an expert. How many data sets do we have in total? So if we want to see what's the size of this data set, let's do data.shape. So there are 2080 samples, and there are 6 columns. So 2080 rows and 6 columns that we have in this data set. Let me go ahead. Let's look at how many samples do we have per class. So there are 4 categories, there are 4 facies. 759 belongs to carbonate, 660 belongs to sandstone, 580 belongs to shale, and then there are some unknown facies, almost like 78 samples. So the whole objective here is to develop a classifier. To develop a classifier, we need to break this data or split this data into features and targets. Features are the inputs, targets are the output, and that's what I do over here, where I take a log transform of resistivity. So anytime you have a feature that ranges orders of magnitude, it's best to do a log transformation on such features. This is a very simple data preprocessing, but data preprocessing is very involved task. And again, if you want to know more of what different data preprocessing we can do on such data sets, do try to join that course, the 2-day course. So here I just converted the resistivity into a log format and added it into this data set. I removed the original resistivity and I removed the well ID. I don't need that for classifier. There are 4 features now: gamma ray, bulk density, neutron porosity, and log transform of resistivity, and we'll try to relate it to the facies. Let's go ahead. Let's look at the distribution of the data. How does the data look like? Before we do anything in terms of model development, we need to visualize the data. There are a lot of dimensionality reduction techniques that can be applied. In this case, I'm just applying a 2 by 2 kind of a representation. I'm putting the data in 2D. It's not a dimensionality reduction. This is just showing the 4 facies distributed across 2 features. What we see, there are a lot of outliers in this particular data set. The distributions are bimodal mostly, and there is a very skewed distribution over here that needs to be fixed before we develop any classification method. If I plot this as a log, it will look something like this. So as a function of depth, we see all these 4 facies distributed. There is a carbonate facies, there is a shale facies, and then sandstone has a lot of carbonates in between. So let's learn this relationship. I'll import some more functionalities. This will break the data into training and testing. Then we'll do some pre-processing. I will do robust scaling and isolation forest. Why am I doing this? How does it work? Again, those are a little conceptual stuff which needs more time, which I don't have in this half an hour kind of an engagement. In this particular approach, we'll develop a k nearest neighbor classifier. We won't be developing a random forest or a logistic regression. In real world, you will try a lot of different methods. You will optimize each of these models. In this demonstration, I'm just using one of the methods called k nearest neighbor. It has a lot of disadvantages, but again, there are a few advantages because of which it acts as a baseline. So let's go ahead, get these functions loaded up. There are some evaluation metrics. Once we build the model, we need to evaluate how good the model is. So for that, we have such evaluation metrics. In this demonstration, I'll just use F1 score. F1 score is a pretty reliable, easy to use. F1 score of 1 means a good classification. F1 score of 0 means a bad classification. So I'm storing all the features, which are the inputs, in X. I'm storing the output, which is the facies label, in Y. So let's do that. Then we'll split the X and Y that I just created. 25% of the data will be saved as testing, and the remaining 75% goes as training. There is this interesting thing that needs to be done when we perform classification, which is called stratification. Without stratification, generally we have problems with imbalanced data set. After the train test split, we have 15,000 samples in training, 500 samples in testing. Let's look at how the feature distribution looks like for the training data set. We have to compare the feature distribution of the training versus testing. We want the feature distributions to look as similar as possible, or else there will be problems in the generalization of the model. If you look over here, there's a lot of skew in gamma ray. There's a lot of bimodal nature. N-phi looks pretty good. It's showing a Gaussian behavior. A lot of these methods, machine learning methods, require an underlying assumption that the data is Gaussianly distributed. So there are some mathematical formulations that we can go into later on if you're interested. Robust scaling is one feature pre-processing method. There are few steps that we need to do in feature pre-processing, and I do those steps. You cannot do a feature pre-processing or data pre-processing on the entire data. You have to perform it on training. Then whatever you learn on training needs to be applied on testing. So that's what I do here. Step by step, I first scale the data using robust scaler because my data has outliers. So first I scale the data. Then I detect the outliers using isolation forest. Isolation forest is a tree-based method. I will show you how this data looks like once we detect the outliers. So isolation forest is what is helping us detect outliers. We cannot detect outliers manually because the data right now exists in a 4-dimensional space. A real world example will have data existing in, let's say, 50 or 100 dimension space. It's very difficult to detect outliers. So isolation forest is a very easy tree-based method that is applied. There is underlying foundation of why isolation forest is good for outlier detection. In this case, I'm applying it. There's a lot of tuning that is needed to detect the outliers properly, and all the blue dots that you see here are the outlier samples. I'll remove the sample so that I create a model based on inliers. Outlier doesn't mean that the data is bad. So this cell over here is all the pre-processing that needs to be done. So I'm doing those pre-processing. Due to lack of time, I cannot go deep, but I'm pre-processing the training, pre-processing the testing. And after that, my training data set is ready. This training data set, what you see here is the feature. The features are scaled and the features are only the inliers. We have removed all the anomalous behavior samples. We have 1529 samples in this feature set. We'll use that for training. And this is the target. We will relate the features over here to the target. And the target are the faces. In this case, the faces are distributed as strings. In a real world implementation, I will recommend using numbers rather than strings. And I will encourage all of you to do a one-hot encoding. Now here, I am building a k-nearest neighbor classifier to relate the features that I just showed you. This is the training features. I'll relate features for each sample to the target, to the faces. So I'll run the cell. One of the biggest tasks in any machine learning model development is what is the right hyperparameter for a given model. I'm using k-nearest neighbor. It's taking some time. It's done. I'm doing a very quick and approximate tuning. In the course, we'll go deeper into how to tune these models properly. And once I tune the model, let me just show you where I'm tuning here. K-nearest neighbor classifier, that's the model that will relate the features to the target. There are two hyperparameters that I'm tuning for this quick demonstration. One is the nearest neighbor, and the other one is the distance formulation. These two hyperparameters, they control the complexity of the k-nearest neighbor classifier. So we tune them to find the right complexity of the model for the data. We don't want to create a very complex model. We don't want to create a very simple model. The sweet spot is right somewhere in between. Each data, each task will have its own optimum model, and that's what I'm trying to find here. Let's look at how for different nearest neighbor and different p-values, how the performance of the model is distributed. So for example, if you look at this row over here, this is when the number of nearest neighbor is equal to 1. When number of nearest neighbor is equal to 1, the classification performance in terms of F1 score is 1, which means this is amazing memorization of the model. The model has memorized the whole training data, but that doesn't mean anything. We have to look at generalization. So this is where I generate a generalization plot. If you look at what is the performance for nearest neighbor equal to 1 in terms of the testing data? Does it generalize well? If you look at this color, it is all 0.875. So the gap between the generalization that you see over here and the memorization that you see over here is pretty large. Memorization is 1, generalization is 0.875 when the number of nearest neighbor is equal to 1, which means you have created a very complex model for the data set. It is learning everything in the training, but it fails on the testing. And that's the biggest problem in any machine learning workflow. We have to find that sweet spot. So in this example, when I compare, there's an automated way in which you can compare and try to figure out where the sweet spot is. For me, the sweet spot lies when the number of neighbors is equal to 7 and the distance formulation is 5. When p is equal to 2, that's a Euclidean distance. When p is equal to 5, it's a fifth order distance formulation. What is that? We can go into that when we, if all of you attend the course. So here I have defined this model based on the optimum hyperparameter that memorizes pretty good, but it doesn't memorize till 1. It memorizes, let's say, around 0.9, and then it generalizes around 0.92 or something like that. So it's a good balance between the complexity and simplicity. So let's look at the accuracy in terms of memorization versus generalization. This is classification accuracy. I can use F1 score. Let's look at F1 score. F1 score is 0.91 and 0.90. From my limited experience on such classification tasks and regression tasks, what I would strongly recommend is if you want to create a model that generalizes well, try to minimize the difference between the memorization and generalization and try to push these two values as close to 1. So reduce the gap and push them as close to 1 as possible. Pushing both of them close to 1 is really difficult. So any value greater than 0.9 when both of them are close to each other is a really good model that you can apply on real world data with some confidence. So with that, what we can do is let me quickly go ahead with a demonstration of a neural network on predicting subsurface property. This is a regression task. And once I'm done, we'll take some questions. And that will be the end of today's discussion. So here I'm building a regressor. What I showed you earlier is a classification task. Here I'm building a neural network regressor. So let me bring in the regression technique that I want to use, which is MLP regressor. MLP regressor is a fully connected neural network. There are a lot of different architectures that you can go for. In this demonstration, I'm using a very simple architecture. I'm importing the data from XLX file. Pandas can read CSV, it can read text, it can read a lot of different formats. So XLX is only for purposes of demonstration. And in this data set, there's only one sheet, and I'm making the column 3 the index. So anytime you import the data, it's very good if we can make one of the columns the index. That index will help us separate different samples. The whole objective of a machine learning task is to relate features to the target for each and every sample that we have in the data set. So let's look at this data set. Depth is the index. The reason it became the index is because in the read Excel file, I have specified which is the index when I'm reading the data. This particular function, read Excel, is a very complex function. It has a lot of innovative functionalities that can help your data importing real good. So it makes your life very easy. So read Excel is a very powerful functionality. So there is some features that have been measured. These are descriptors, these are predictors. So shaliness, saturation, integrity, and pore volume. These 4 properties needs to be related to the photoelectric factor. If we can do that, we can very easily identify different lithology in the subsurface. Photoelectric factor is a good approximation of lithology. And here we are building a model that can relate these 4 to the target, which is photoelectric factor. A real world data will be really huge. It will have a lot of columns. It will have a lot of samples. In this case, we have a very small data set, only 830 samples, where there are 5 columns, and one of the columns is the target. So I get my features. This is the feature. I get my targets. So from the original raw data set, I get my features and targets. Then I perform the train test split. This is a regression task, so stratification is not needed. And there are a lot of different ways to perform stratification. I'm using robust scaler. In the real world application, you will have a lot of different options to choose the scaling. And each data set, depending upon its characteristics, depending upon how many outliers are there, will require a very specific type of scaling. In this case, for purposes of demonstration, I'm just using a robust scaler. Now here, I'm build a MLP regressor. This is the neural network. And in this neural network, I'm defining how many layers should be in the neural network. So I'm defining there are 3 layers. The first layer contains 20 neurons. The second one contains 20 neurons. And the third one contains 30 neurons. Neurons is where we will have a multiplication followed by summation followed by an activation. So generally, a neuron performs a very basic linear algebra operation followed by passing all the value through our activation function. So this particular neural network has 3 layers. The training data set has around 600 samples. Out of those 600 samples, I'm using 100 samples during each iteration to train the neural network. So during each iteration, 100 samples will be picked randomly and they'll be used to train the neural network. And I'll perform those iterations over and over again. And for each iteration, I'm not taking the entire 600 samples. I'm taking 100 out of the 600. The reason is we want to create a model or we want to create a neural network that sees different portions of the data and builds a relationship between features and target by looking at different portions of the data. We want our model to generalize well. The problem with neural network is they are very complex. They can very easily memorize. So things like batch size is needed to reduce the complexity and make your neural network generalize well. In this case, I'm not performing any optimization of the neural network. I'm straight away saying that use 3 layers, and the first layer has 20 neurons, the second has 20, and the third has 30. In real world, we won't do it like this. In the course, what I show is how we can optimize this entire neural network where we can try different layers, different number of neurons to find the right neural network for the dataset. There is an activation function which we use here, which is RELU, rectified linear unit. Early stopping helps avoid overfitting. How does it help avoid overfitting? That's a slightly deeper concept which we can go through during the course. Alpha is the regularization. Each neuron needs to be regularized. We don't want a neuron to memorize too much. So there's a regularization term that we apply to each neuron. We are performing 6,000 iterations. If there is some overfitting, then the iterations will stop and you will come out of the loop. That's what early stopping does. So let's run this neural network on the data set. And then during Q&A, we can go a bit deeper into why I chose these particular values. But in real world, we have to optimize. We cannot just use a static description of all these different hyperparameters. So here I'm learning from the training data set. I'm learning from the scaled training data set. The goal is to relate these 4 properties, which are the features, to the target, which is the photoelectric factor, which defines the lithology of the rock. Let's look at how this neural network performs on the testing data set. What you see here is R square. R square of 0.65 is a poor performance. It's not a great performance. I can also show a mean absolute error. Mean absolute error generally is in the same dimension as the photoelectric factor. We can make this mean absolute error a bit better by normalizing it with respect to the variance in the testing data or by normalizing it with respect to the mean of the data, which I have not done here. I'm just using mean absolute error, which has the same unit as the target. Now I'll show you one quick thing. I'm running the same thing again and look at the neural network score. It changed. Let me run it again. 0.64. So the testing data is the same. I'm not doing anything with the testing data, but the performance of this neural network changes a lot from 0.55 to 0.66. So what this shows is whatever you're learning is not scaling well. You're not learning a thing which is ready for generalization. In a real world scenario, we'll not just build one model which is tuned to the data. Rather, what we'll do is we'll generate a probabilistic distribution of the performance of the model. And what I'm showing you here is without changing anything, you are seeing a variation in the score from 0.55 and now you have close to 0.7. By optimizing these hyperparameters over here, we can improve this performance close to 0.8, and we can reduce this variance that we are seeing in the neural network. The variance is because what you have done is you have created a complex model. You need to simplify. So with that, we'll end today's kind of demonstration. I have two more cases, but those cases are only for data manipulation. One case over here is exploratory data analysis on a large petroleum data set. How can we do that? How can we generate some interesting visualizations? And the other one I had is all about simple array manipulation to get what you want. So let's say you want an average rate at each location in the month of January, how we can do that. But for this limited interaction that we're having, a case study on the classification and a case study on regression from my point of view is kind of a good starter for all of you to think more on how to build good machine learning algorithms. And if you are interested in learning more about the concepts, the foundations, how to tune, how to ensure that the variability of the model is reduced, how to reduce the probabilistic predictions of the model to a narrow range, then I strongly recommend all of you to attend the course, which is organized through SCA in the month of January. With that, I'm open to answer some questions if there is any.
Great, we're starting to get questions now. We did have a question about how we're going to share the recording of today's webinar. And later today, attendees will receive a link to the recording. You'll receive an evaluation form and a link to register for Introduction to Subsurface Machine Learning that's scheduled January 16th through 17th in Houston, Texas in a public class. I'll also mention that SCA's website, scacompanies.com, has an on-demand webinar library. And so this recording will also go on our website. And you might want to peruse the other webinars that are posted there. I think we have over 50 that we've recorded over the years from various instructors in their classes. So we have a question from the question feature. For your neural network, you have early stopping set to true. How will you know if it is overfitting while running? You're on mute.
Thank you. So that's a great question. And in a limited kind of a time interaction, it's very difficult to show what happens when you make this thing true. But all I can say is early stopping, when you activate it to true, it will split the data into training and validation. So you first split the data into training and test. You have done it already here. And that training data will be further split into training and validation. As the model goes through these iterations, it is learning from the training part of the data, and then we test this model on the validation part. Once we start seeing a big difference between the training portion and the validation portion, once we start seeing that the validation score starts increasing, that's an indication that you are creating a complex model. What do I mean by complex model? What do I mean by model which is memorizing too much? What I mean by that is when we define that this neural network has 3 layers and so many neurons here, how many degrees of freedom we have here? Roughly speaking, we have 20 into 20 into 30. Roughly speaking, we have around, let's say, 12,000 degrees of freedom. You are trying to learn 12,000 degrees of freedom on a small data set, which is only 800 samples. So when you have so much of degrees of freedom, early stopping will keep a check whether the validation performance is increasing or decreasing. And once it starts seeing that the validation performance is increasing, it means your neural network is starting to memorize. So that's when it will come out of the loop. So I hope I answered that question.
Next question, did you compare your results with other commercially available tools like data analysis models in Petrel or Techlog?
To the best of my knowledge, when we develop a good workflow in let's say Python, using all these different packages that I showed you right at the beginning. So for example, here we are using 4 packages, which are go-to packages: NumPy, Pandas, sklearn, matplotlib, Seaborn, and then I showed you some functionalities. Once you create a good workflow using those packages and those functionalities in Python, we can create a plugin, a Python-based plugin. And to the best of my knowledge, all these Python-based plugins are then converted into C# for faster computation, and then they go into the Techlog and other softwares. So basically what I'm trying to say here is this is the starting point for proof of concept prototype development. Then you convert into C# or something that allows you faster computation on large data sets, and then that becomes a plugin in commercially available software. If you develop a good model that generalizes well, then the platform doesn't matter. It's all about the workflow, how much time you have put into designing good feature set so that you can relate the feature set to the target, and then you have to evaluate your performance. And that's what the focus of this entire 2 day of course is. How do we create good models using the features, the targets, and the evaluation metrics that we have access to?
Next question, are you able to use machine learning to do the following? Identify wells that will quit, predict hydrocarbon intervals based on seismic input information as input.
So machine learning, if I have to explain what machine learning does, what I would say is it's trying to relate. It's trying to find a statistical function that can relate X with Y. If you can describe your data in terms of features, in terms of targets, and if your features and targets are representative of the system that you want to understand, then you can connect any X with any Y. It doesn't matter what the X is, what the Y is. Machine learning is all about trying to build the bridge between the features and the target. So machine learning has been widely used in the seismic domain and the geophysics domain to speed up existing workflow, to automate existing workflow. Uh, in an existing workflow, there's a lot of intervention that we as experts, we need to make. So how can we automate some of these interventions, to avoid the biases, to free up the time of experts so that they can think deeper into the concept and focus less on the manual tasks. So automation is one of the reasons why machine learning has been widely used in the seismic domain. And if you come towards the production side of things, performing uh, reliable decline curve analysis, designing precision engineering. For example, how should a particular tool uh, measure for how long at a particular depth if you want to observe a particular phenomena. So that's called precision engineering. So ML has been used for precision engineering. It has been used for production forecasting. It has been used for increasing the speed of simulations. It has been used for automating mundane tasks. If there's a task that you do over and over again, and it's very mundane, it takes, let's say, around 10 seconds to 15 seconds of your time to do that task, then let's replace that task with an ML algorithm, which has been widely adopted in our industry, automation.
The next question, how easy is it to learn both Python and subsequently machine learning?
I regularly teach this 2-day course to a lot of people with very limited experience in Python and in machine learning. So this course is designed to satisfy both the needs, learning machine learning as well as learning how to code. I provide all these workflows, these pre-built scripts that you can run and learn from it. The beauty of this course is it kind of channelizes your thought, it channelizes your energy into things that can give you a quick success in limited time. But the world of machine learning, the world of coding is very vast. I personally, I don't know everything that's out there, but what I try to do in these courses is channelize the entire attention of the participants into things that will give you quick results so that you can go from a beginner level to at least close to an intermediate level. So that's my whole objective, taking you from beginner to intermediate. And that's a pretty difficult task in just 2 days. But I've received some good feedback over the time. So this entire course is designed to satisfy that. Um, how can you kind of learn both of them together? My recommendation is to do any type of ML work, you need to know coding. So you cannot do ML work without knowing how to code the basic level. And coding in itself is a skill that you learn over time. It takes at least a month or 2 months to just get yourself familiar to writing scripts that don't break down. And once you learn the coding part of things, then you can start writing the machine learning aspect. But one last thing that I would like to point out to the audience over here who are slightly afraid of coding. Let me go to MLP regressor right over here. So let me go to MLP regressor right over here. This is where I'm defining all the hyperparameters, and this is where the learning takes place. Now, if you unpack the code, what is happening here? If you unpack the code here, what is happening when you learn or when you try to fit MLP regressor on the training data? That is very intense. That cannot be learned in just in a 2-day course or let's say in 6 months. To know what happens in the back end, it needs a lot of practice. But the good thing is there are a lot of beginners like us who can just use these simple statements, simple commands to get to a basic level without knowing what is the optimization algorithm behind, which helps us learn this entire relationship. So there's a lot of computation that happens in the back end. You can only see it when you unpack, unzip what is happening here in this course or in your day-to-day work life where you're trying to use these techniques as an engineer or as a scientist. You don't need to unzip and try to see what's happening behind the screen. If you just learn these basic scripts, you will be ready to build models that can generalize well. And then you'll take it to the next level where you'll start working on large data sets using very complex methods such as neural networks or gradient boosting.
So you mentioned using the isolation format to detect outliers. The next question is, can we eliminate outliers by assigning min and max limits?
Yeah, so min and max limits can be assigned. So in this case, I showed you the use of isolation forest as a data preprocessing technique. Data preprocessing techniques need to be applied in a particular order. You cannot just apply it blindly on the entire data set. There is an order that needs to be followed or else you're biasing your model. So let me show you this isolation forest right over here. So I am using isolation forest that will help me detect outliers. I am defining how many trees are there in this forest, what's the level of contamination, and there are other hyperparameters that we need to define. So this is not a single instance. What are you seeing here is a single instance of the outlier detection, but in real world, you'll apply different instance. You'll try to figure out which instance of isolation forest performs the best for your particular data set. What it does is it tries to find the outliers which are isolated in a high dimensional space. Min-max, when you define those values, you have to define min-max for each and every feature. And maybe when you define min-max, they are not truly isolated from the rest of the data. So to find isolation, there is isolation forest. To find relative density or to find regions which have low density, there is uh, a method called one class SVM, or there's another method called local outlier factor. They try to find regions with low density. So depending upon how you define your outliers, there's a very specific technique that you can use. And min-max that you mentioned is the beginner level technique to find outliers. That is also called thresholding. Thresholding has a lot of disadvantages, but if you just want to do a quick dirty outlier detection, then what I would recommend is generate a histogram, find your min and max values where you want to clip. Generally, let's say it's 2 percentile and 98 percentile, you'll clip your data set at those percentiles and you will build your outlier detection. But if you want to take it to the next level, isolation forest, local outlier factor, one class SVM are the next level outlier detection that look at the entire data set in the higher dimension, and then they try to figure out the outliers. They don't do it one feature at a time. They take multiple features into account to decide whether it is a true outlier or not. So, yeah.
So the example you've shown today is well-logged data. Can you start the processing from the LAS file, or do you have to convert it to Excel?
The packages that convert from LAS to the format that you want to use it on. There are a lot of packages that have been developed by experts, which are publicly available as an open source package. Some of them may need some licensing agreement. So I would recommend look for LAS reader or LAS format converter. So there are a lot of packages like that. So let's say if you find a package that can work with LS data. So what you'll do is you'll go to this particular step. Uh, Prior to this, you'll create a cell, and here you'll import the package. Let's say, I'm just kind of naming a package. Let's say import LAS reader as LS. And then once you import it, depending upon what are the different functionalities, maybe there is a functionality which is convert LAS to Excel. Let's say there's a functionality like that. So here you will define your log format as a LAS and it will get converted into Excel. But I don't know whether a package named LAS reader exists or not, but I know there are packages developed by experts which can read LAS files, convert it into the format that you're interested in. I'm just defining or describing a simple example of how you will do it, how you will, let's say, convert a LAS into Excel if there is a package called LAS reader with a function which is, let's say, convert LAS to Excel.
So next question, do you run courses on Python as well? I think it's one of our listeners today is asking, do they need to have any experience with Python to be able to take your introductory class?
Yeah, a little introduction is needed, but the way this two-day course is designed is to take beginners and get them comfortable with both Python and machine learning. Um, I generally teach a lot of Python programming for petroleum engineers and geoscientists, so things like that can be arranged for sure.
Great. You mentioned that in the class you have two problem sets. Can you talk about the types of problems that you would be solving in the standard public class? And if one were to have it in-house, could you substitute an in-house example?
Yeah, so there is a project for production forecasting where we work with a specific data set where there are operational parameters, there is historical data. So we'll combine the historical data with operational parameters to learn to predict, let's say 3 days in future, 10 days in future. It's a really difficult task when you try to predict how the flow will behave 3 days in the future. So we generally keep it 1 day in future, 2 days in future, 3 days in future. So this is one example where we can build a model for forecasting. The other approach that we can have over here is replace traditional decline curve models with something like gradient boosting regressor or neural network. But whenever we work with time series data, we have to be very careful. All the examples that I showed you today is based on depth-based data, where the assumption is nearby depths don't influence each other. So that's a big assumption. In real world, a depth-based data is also connected as a function of depth, just like a time-based data. So when there is connection between each instance of time or each instance of depth, your approach needs to be slightly different. You cannot use traditional workflows for such data sets. And then there is this project on shale image analysis, which is working on a spatial data. There's a large image. So how to read an image file, how to get to the pixels that you're really interested in, how to extract features from such an image so that you can build a model that can locate, let's say, where is the matrix, where's the pore, where's the kerogen, where's the pyrite. There's just a demonstration of working with image, which is a spatial data in X and Y. These data sets are large, and you have to extract features and build a model so that we can detect the regions or the material of interest in the image. So these are two projects that I have in this particular course. They're pretty well designed. In terms of the 2-day course that we have, we kind of cover everything from NumPy to pandas to visualization, building regression using sklearn. Then, as I mentioned, feature selection, dimensionality reduction, very important concept. Clustering, outlier detection, another important concept. These models are probabilistic. They will show some range of uncertainty, so how to quantify them properly, and then how to build complex models so that they generalize well. These are the areas that we focus in this 2-day course.
So you're showing right now some optional add-ons. I think that could be for an in-house course where you might have some group projects. Can you talk a little bit about how that might work for an in-house course that could be spread over more days?
Yeah, so these two examples that I mentioned, they are pretty intense in the sense it needs a little time for the users to develop. So all the participants, once you get familiarized with these concepts in 2 days, then you'll be given 1 week of time to build a model for production forecasting. Uh, you'll be provided with some guidance, and once you build the model, I will show you what kind of model I have, what was my approach, so that will give you understanding of what kind of workflow I have come up with based on my experience versus what you came up with. Similarly, for the next week, what we can have is I'll assign you the data set. You work on this shale image analysis. You're working in group. It will take some time for you to coordinate to build a model that generalizes well. Once you have your workflow, you can compare your workflow with mine. So that's the whole objective. Do a little bit of development on your own and then compare what you have with the workflow that I have built. And we'll try to reach to a level which is good for a beginner level. What I mean by that is whatever you see here, it cannot be commercialized right away. So these are not ready for commercial deployment. What you have is a proof of concept that will need a little more tuning, a little more improvement before you can do anything commercial with these models.
So you mentioned the importance of pre-processing data. How much time do you spend in pre-processing data?
Yeah, it's a pretty intense task. Pre-processing takes almost like 60% of the entire machine learning workflow. So pre-processing is 60%, model evaluation is 30%. So what you're left with is 10%, which is the machine learning model development. What I want to emphasize is a lot of time goes in cleaning the data, getting the data ready, getting the data in the right structure so that you can build good models on it, 60%. Once you build your model, how to evaluate whether it's working or not before you deploy it, 30%. And what you have remaining is that 10% where you're trying to optimize your various techniques for your task, for your data set.
Excellent. Well, I'll give our listeners one more chance to ask a question, and I'll just thank everybody for attending today's webinar. Reminder, later today, you'll receive a link to the recording of today's webinar, an evaluation form, and a link to register for Introduction to Subsurface Machine Learning that's scheduled for January 16th and 17th in Houston, Texas. So thanks very much for your time today, and we look forward to seeing you at the class in January. Goodbye.